Hi friends, welcome to follow up. Let's have a look at problem 1458, max dot product of two subsequences. In this video, we are going to explain two formats of solutions based on dynamic programming. So here we are given two arrays, nums1 and nums2. So we want to find the maximum dot product between non-empty subsequences of nums1 and nums2 with the same length. So here the important assumption is that we want to consider all non-empty subsequences. So the third paragraph basically explains what's a subsequence. So here are three examples. In the first example, so we can take 2, -2 and 3, -6. So this will give us 18, right? So in the second example, so we can take 3 in the first list and 7 in the second one. So we get 21. And in the third one, because the nums1 contains all negative numbers and nums2 consider all positive numbers, they're the same. So we just need to pick 1. So this also explains the assumption that we need to consider non-empty subsequences. In other words, for this one, the maximum possible is -1. The constraints are the following. First, the two arrays have length bounded above by 500. And for the elements in the two lists, so they can be negative, can be positive, and also can be 0, right? So here, the second assumption is sort of important. The reason is that, there's negative numbers, right? So with that said, we are ready to do the analysis. So for this problem, actually, there are a number of ways to solve it or address it. So here I'm going to use dynamic programming. So here I'm going to make a 2D table. So dpij can be interpreted by different ways. So here I'm going to say maximal dot product of non-empty subsequences up to index I and index j respectively, right? So here we can choose to include the two indices I, j or not. So here I'm going to make a so let's assume the two lists are A and B. So here let's say length A is m, length B is n, right? So I'm going to make a m plus 1 and times m plus 1 table. So for this, I'm going to consider this max dot product up to index ij, but not included. So in other words, we end at index I minus 1 and j minus 1 due to the range of ij, because here if we do this table, so I will run from 0 to m and n will run from 0 to n, right? N and m and n is the length is one larger than the index of the elements in the two lists. So with that said, we are ready to do the coding, but the key thing is how do we do the update. So for this purpose, let me first write the steps. So initialization. So for this initialization, so I'm going to do this. So I'm going to set all the things to be, let's see, float. So I'm going to use a negative infinity, then times m plus 1. Then for so here float infinity. So for a dummy index running from 0 to n, right? Let me write it like this. So this will be our initialization. Notice that in this table, the first row and the first column, in other words, the rows and the columns corresponding to index 0 is negative infinity. The reason is that this corresponds to one of the so they do not have element. You can interpret it like this. and then we are going to do the update. So for this, the update will be the key. So for I in range, so I'm going to start from 1 to m plus 1, and then for j in range 1 to n, so we write 1 up to, but not include m plus 1. So for this purpose, let's update dpij, right? So we want to take maximum because we want to find the maximum possible one. So here we can choose to use the index I-1 and the index j-1 elements in the two released as the ends. We choose to use it or not. So if we use this and make it a pair, so it's a at index I-1 times b j-1. So in this case, so we want to we use this pair as a corresponding component in the final dot product. Then in this, we want to add the maximum possible before this one, that is I-1 and j-1. So here you need to pay attention to the interpretation of this dpij or dpi-1 j-1. So this is the one possibility. Another one is that we do not choose the previous one. We just consider a I-1 b and j-1. So this actually corresponds, you can digest this using example 3, because we need to make it non-empty. We need to at least choose one. So we can choose this pair. And then if we do not use the two pair, so we can compare with dp. So we do not use I, so we use this one. This is much possible. And then we do not use the j-1 index. In other words, do not use g, so we get dpi j-1. So this is the dp update rule. This is the main formula or recursive relation. And then after this, so we can do the return. So we want to return dp return. So here I didn't write. So let's first make m n to be length of a, length of b, right? So here we want to return dp at m n, right? So notice that the m and n are not in the rigorous the index of the elements, but the size. So that's actually a solution to this problem, or a format of dp. So before we make any further solution, let's first do a test. Yeah, it passes the example 3. So now let's look at the generic case. Yeah, it passes all the cases. So I would say for this problem, once you realize the recursive relation or recurrence relation, so it's actually rather straightforward. So however, in this problem, so we use a format of dp. In other words, we used table, dp table. So let me write another solution to slightly change the format. So here I want to use this one as v1, and then let's copy this part, this one. So what I want to do is that we want to follow the same merit or spirit, but we write a slightly different format. So here I'm going to use dp, I'm going to use collections, I'm going to use default dictionary, and then we want to set default values. So here I'm going to say lambda. So I map everything into float negative infinity, right? So this is like here, the first row, the first column, right? And then I just need to iterate for I in range m and for j in range n. So here I and j are indeed indices. So and our dp interpretation would be the maximum dot product of non-empty subsequences up to indices I and j, both inclusive, right? So in this case, let's do the update. So dp, so here ij, so I'm going to use the coordinates or tuple of the indices as a key. So in this case, I'm going to do max, right? So we can do ai times bg. So in other words, we use this pair as a part of the dot product. So in this case, we are going to write I minus 1 and g minus 1. So here we don't need to worry about if I and g or g is 0, because if this k as a tuple does not inside the dp table yet, it's going to have a value that is negative infinity. So this is one case. So here we use this pair as a corresponding components in the two subsequences. And also the second one is I want to use this AI and BG themselves. The reason is that we want this two sequences to be not empty. So if we include this pair, at least we have a length 1 subsequences respectively. So then the other one would be dp I minus 1 g and dp I g minus 1, right? So afterwards we can do the return. So here we want to return dp, so we can return so what we want to return is dp length, and we write m minus 1 and minus 1, right? So this is the second solution format, essentially the same, but here we use this default dictionary. So before we make further comments, let's first do a test. Yeah, it passes the third example. So now let's look at generic case. Yeah, it passes all the generic cases. So with that said, basically that's about it for this specific problem. So for this problem, when I do the problem myself, I found that this assumption, not empty, is very important, because some people might forgot this piece, this ai minus 1 times bg minus 1, or here ai times bg. So this incorporate or take into consideration of the non-empty assumption. So basically the other three pieces, so it's very easy to digest or observe or include if you have done problem like longest subsequence and the minimal number of deletions to make two strings equal, the problem like this. So with that said, that's basically about it for this video.